Hi everybody, I hope this video finds you well. Today we're going to be sort of finishing up section 2.2 from your textbook, finishing up our discussion of talking about the algebra of matrices. In the last video we sort of introduced and talked a little bit about defining matrix multiplication. We're going to do a little bit more with that and specifically see how some of the operations like matrix addition and matrix multiplication mix with that operation that is exclusively defined for matrices, which is the transpose. So we're going to talk a little bit about some properties of the transpose. So the first property we're going to mention here is that if you take the transpose of the transpose, you will return to your original matrix. That should make sense. If the transpose is interchanging row and column, and then you interchange again, you should get back to where you started. The second one is that transpose distributes over addition, so that the transpose of A plus B is A transpose plus B transpose. And finally, for property 3, that transpose also distributes over multiplication, but in sort of a weird way. It actually becomes B transpose A transpose. So transpose distributes over multiplication, but as you can see, if it's A times B, it becomes B transpose A transpose. So it changes the order of the multiplication. Now again, on all of these, right, we're making the assume that the operations are well defined. So in other words, in something like this, right, A and B have to be the same size, and here the number of columns of A has to match the number of rows of B so that the multiplication makes sense there. Right. Now, if you look in your textbook, this guy is proved in book. So we are going to go ahead and prove this guy here. I'm going to prove this one now. And I would recommend, once you've read the one in your textbook for how to prove property 3, and once you've looked over the proof we do for property 1, see if you can go ahead and create one for property 2 there. So let's go ahead and take a look at how we would prove property 1. So the proof of property 1. So what we need to show, right, is we need to show that A transpose transpose is equal to A. Now, for A transpose to equal A, just like we've been doing, we're sort of doing by element proofs. So we're going to show that each element of these two matrices are the same. So we need to show that A transpose transpose has its ijth element equal to the ijth element. Oh, and sorry, my notation's a little sloppy there. That needs to be equivalent to the ijth element of that matrix. And again, that bracket notation is not essential. It's just helping us sort of visualize what we're doing. We could just say A sub ij with no brackets here whatsoever, right? But the brackets hopefully make it a little bit easier to read. So we're going to try to do this proof from sort of this left-hand side and work our way to this right-hand side. Okay? So our actual proof here, well, we're going to take a look at what we can sort of say about the ijth element of this matrix. Well, as you guys know, if you're looking at the ijth element of a transpose, that is the jith element of what matrix you were actually transposing. So we can say that this is equivalent to the jith element of A transpose. You'll have to apologize. The barking in the background, dog does not appreciate the transpose, apparently. He's just not that sort of dog. We've got this statement here that says that if we want to understand the ijth element of this transpose, then we just need to look at the jith element of what we're actually trying to transpose. But now that we have that, we can actually go ahead and say, okay, well, what do we know about the jith element of this A transpose? Well, it needs to be the interchange of the original matrix. So this would be equal to ij of the original matrix A. Well, if you look, that shows that this is equivalent to this, which is equivalent to this. So we've shown our actual result there. So that's our proof. We put our little check mark, we can put a QED there, and we're all good. That's a very sort of simple example of another proof by element. Much nicer than that proof about sort of the associativity property that we did for multiplication of matrices. But again, this is sort of the most fundamental way to prove something about a matrix, is to prove it via the elements. All right, the next thing we're going to do is we're going to show another sort of proof strategy based on matrices. If we just go back for a second and take a look after that proof, we now have some properties established about the transpose. So what we're going to do in our next example is actually prove another property, not from scratch, not from using the elements, but actually from using these properties. So let's go ahead and look at that. What we're going to do is we're going to do an example of a proof by property. And what we're going to try to do is we're going to try to prove that if you have three matrices, A, B, C, multiplied together, and you take their transpose, that this is going to become C transpose, B transpose, A transpose. In other words, what we're going to try to do is we're going to try to extend one of those results about the transpose to not just a product of two matrices, but to a product of three matrices. And we're going to do this as a proof by property. And what we mean is we're not going to go to the actual elements. We're going to try to use the properties that we have. So let's actually try to do this. So our proof. All right. So we're going to start with A, B, C transpose. And then just for sort of the sake of convenience, or to just make it visually a little bit easier, let's sort of group this. We're going to think about this as AB, sort of as a single matrix, and then C, and then transpose. Now we have a property that says if you have the transpose of a product, which we now do, then that transpose will distribute over the product, but it'll change the order. So this will be equivalent then to C transpose and then AB transpose, because we know that the transpose, when it distributes over a multiplication, changes the order, and then each has its transpose now. Now, if you think about this term here, now this transpose is applying to another product of two matrices, and we know how that works. So this would become C transpose, B transpose, A transpose, because once again, when this transpose distributes on that product, it changes the order, and each one gets a transpose. So that's exactly what we wanted to show. We were able to show that ABC transpose is the same as C transpose, B transpose, A transpose. So that's our proof. QED, and put our little check mark. Now you might ask yourself, wow, that seems a lot sort of more straightforward than some of these proofs by element. And this is, of course, why we establish some of these properties. If we have properties ahead of time, proving something doesn't require us to go all the way back to the strict element definition. We can instead prove by the properties that we've established. But of course, that requires that we took the time earlier to establish these properties. So one thing you guys will sort of see is that sometimes these proofs that you'll be asked to do in class might be saying prove it by going all the way back to the elements, so a very, very sort of fundamental proof, or it might ask you to prove by properties, so you're allowed to assume any of the properties that we've sort of established in class. All right. We're going to continue and introduce a few more sort of theorems or concepts, again, sort of focusing on the algebra of matrices and how it relates to some special types of matrices that we've encountered already. So let's go ahead and talk about that. So we're going to talk about some results for lower triangular, upper triangular, and diagonal matrices. So what we're going to do is we're going to just sort of establish three results here. So one, if A and B are both lower triangular, or they're both upper triangular, or both diagonal. So in other words, if you have two matrices that are both lower triangular, or both upper triangular, or both diagonal, then A plus B will be lower triangular, or upper triangular, or diagonal. So in other words, if you start with two matrices that are lower triangular and you add them together, the result will be lower triangular. If you start with two matrices that are both diagonal and you add them together, then the result will be diagonal. In other words, adding matrices that have one of these special formats preserves that format. Okay? If AB are both lower triangular or upper triangular or diagonal, and K is a non-zero scalar, So k not equal to 0. Oh, we don't actually, my apologies, we don't need two matrices in this one, so let's just go ahead and erase that real quick. It wouldn't be wrong, but we don't really need it. So let's say if A is lower triangular, or upper triangular, or diagonal, and k not equal to 0, so just non-zero scalar, then ka. Well, why do we need, I mean, the 0 case is trivial, so let's just get rid of that as well. And k is a scalar. If it's 0, then the whole matrix is going to be 0, so it's automatically lower triangular, upper triangular, diagonal, so we don't need that non-zero restriction. And k is a scalar, then ka will be lower triangular, or upper triangular, or diagonal. So this is just saying that if you start with a matrix A and you have it that it's lower triangular or upper triangular or diagonal, then multiplying it by a scalar will keep it in that same form. Finally, if A, B are both lower triangular or both upper triangular or both diagonal, then AB will be lower triangular or upper triangular or diagonal. So in other words, if you start with a couple matrices that again both have that sort of special property of either both being lower triangular, both being upper triangular, or both being diagonal, then multiplying the two matrices together will preserve whatever that special property is. Now, in your textbook, they go ahead and they prove 3 for LT and UT in book. So again, I would recommend going ahead and reading their proof of that. We're going to go ahead and prove property 3 as well, but for diagonal matrices, just so you guys can sort of see that. For properties 1 and 2, these are pretty straightforward, and I would recommend trying to prove those results for yourself as well. All right, so let's go ahead and take a quick look at that proof. So we're going to do a proof of property 3 for diagonal matrices. Now you'll notice that since we're trying to prove this property without recourse to any other, this is going to again be a by element sort of proof. So we're going to have let A and B be diagonal matrices, right? What we need to show is we need to show that AB is diagonal. Okay. Now let's think about what it means to be diagonal. So what we need to show is, if you recall the definition of a diagonal matrix, we need to show that every element is 0 if you are off that diagonal. So we need to show that if we are off that diagonal, if I is not equal to j, then the element of AB is equal to 0. So let's go ahead and prove that. Okay. So to prove this, let's consider AB ij with I not equal to j. If I does equal j, we don't care because there's no restriction for what happens when I does equal j. There's no restriction for what happens on the diagonal. There's only a restriction for what happens off of the diagonal. So what can we say about AB ij? Well, we can use the definition of matrix multiplication to say that that's the sum from k equals 1 to n of aik bkj, right? That's the definition of matrix multiplication. And you'll notice that in this proof, just because we're starting to do more of these and hopefully you guys are getting comfortable with them, I'm just making a note of what allows us to sort of take that step. All right. Now, what we're going to do is we're going to sort of split this sum apart. And it's going to look a little bit weird, but we'll explain exactly what we're doing here. So we're going to think about this now as the sum from k equals 1 to n, but we're going to take out one thing where k is not I. And then we're going to have aik bkj. Now we did take out one thing, so we'll have to add to that where k actually does equal I. So that would be aii bij. Right, so if you want to think about that, this guy right here is the one moment where k does equal I. So we're just sort of stripping this guy out of the general sum. So why do we do that then? Well, let's think about this piece right here. Remember that this right here, that this ij, we're making the assumption that I is not equal to j. So again, we're focused on this portion right there. So since I is not equal to j, we know bij equals 0. How do we know that? Since b is diagonal. Okay? And remember, if you're diagonal, all your elements off of the diagonal must be 0. So we know that that guy is 0. So what we can say then is we now know that abij is actually just equal to this sort of sum from k equals 1 and k not equal to I up to n of aik bkj. Because that whole term back here, well, we know that it's going to be 0, so this whole thing is technically plus a 0 there. All right, now what can we say about this? Well, notice that now we've ruled out k being equal to I. So here, that I and k will never be the same. So what that means is that for all k in this sum, k will not equal I. So aik will be 0, since a is diagonal. Right? If we think about that, what that's saying is that since we ruled out that one moment where k is I, now these two subscripts will never be the same, and since A is a diagonal matrix, that means all those values are 0. Well, if all those values are 0 then this product is going to be 0, and that means this sum is going to be 0. So that tells us that abij is equal to 0. If you think about what we needed to show, right? Well, this was under the assumption when I not equal to j, right? That's what we sort of considered up here, and that's what we proved down here. Does that match what we needed to show? Well, we needed to show that it was 0 when I was not equal to j, and we did that. So AB is diagonal. We'll put our QED and our check mark, and we're all good there. All right, so that was another bi-element proof for sort of a basic property. So in this sort of video, we've seen a couple element proofs, we've seen a property proof. Got to be comfortable sort of working both ways here. The last thing we're going to talk about in this video is just sort of a little bit of a tangent, but it is included in section 2.2 in your textbook, so we should briefly mention it, is how all these sort of operations also would apply if you have a matrix that includes functions rather than just values. So we're just going to briefly talk about an example where you do some calculus on matrix functions. So as a brief example of this, let's just consider, just for the sake of this example, let's say we have a matrix function a of x. Maybe it'll just be a 2x2 matrix function. It's got things like e to the x, x squared. We'll put cosine x there, and maybe 3. Right? So there we go. It turns out you can do all the same sort of operations that we've been sort of discussing, but you can also include sort of calculus-based operations. So we talked about how you can multiply a matrix by a scalar. Well, you can also multiply a matrix function by a functional scalar, right? So you can take your scalar multiplication and you can extend it into scalar function multiplication. So in other words, we could talk about something like x squared a of x. And all that would be is that would be a new matrix function where every element has now been multiplied by x squared. So you'd have x squared e to the x, you'd have x to the fourth, you'd have x squared cosine x, and you'd have 3x squared. So just like normal scalar multiplication, if this guy out here is just a scalar function, right, not a matrix of functions, but just a normal function, then you can just distribute him in onto every element individually and get a resulting matrix function. Okay. You can also take the derivative of matrix function. Is done element-wise. So if we talked about a prime of x, all we would do is we'd build ourselves a new matrix function where we take the derivative of each of these elements individually. So if we did that here, we'd get e to the x, we'd get 2x, we'd get negative sine of x, and we'd get 0, just differentiating each element individually. You can also integrate matrix functions element-wise as well. So if we did some sort of definite integral 0 to 2 of a of x dx, well, what we would do is we would integrate each component. So we get e to the x evaluated from 0 to 2. We'd get 1/3 x cubed evaluated from 0 to 2. We'd get cosine x evaluated from 0 to 2. And we'd get 3, it'd be those last two we forgot to actually integrate. Well, I forgot to integrate. You hopefully did not. We'd get sine x evaluated from 0 to 2, and we'd get 3x evaluated from 0 to 2 after integrating. Then after evaluating, it looks like we'd get the matrix e squared minus 1. We'd get, 8/3. We'd get sine of 2, and we'd get 6, right, after doing those evaluations. So you'll notice that since my example here was a definite integral, we got actually not a matrix function, but just a normal matrix of values there. If we had done a indefinite integral here, then we'd get a very weird thing. We wouldn't actually get a matrix of functions. We'd actually get a matrix of families of functions, because everything would have its own plus c, and you'd actually need to use separate constants for each one. That's not something we really will ever see, so we're not going to bother with an example of it, but you could in theory do that. So that right there sort of wraps up talking about operations on matrices and different ways of calculating sort of matrix algebra. In our next video, we'll start introducing how matrices are related to systems of linear equations, and we'll start seeing some uses for all the stuff that we're talking about with matrices.